The scientific principle that creates Earth's seasons, which is its tilt towards or away from the sun, determines how much solar energy reaches the surface at any moment. As this angle shifts, the amount of sunlight absorbed changes as well. This principle is key to our project. Solar panels are a rapidly growing energy solution, but they face a major drawback. Their efficiency heavily depends on the sun's position. As the sun moves throughout the day, energy output varies significantly. Under the engineering grand challenge of making solar energy more economical, our team, Ethan Minton, Sasha Laka, John Ebert,
and myself, Cameron Beat, was tasked with finding a solution to this problem.
Our objective became clear: design an automated system that could continuously reorient solar panels throughout the day to maintain the optimal angle for sunlight capture.
Now, how exactly does one achieve such a system? Our team identified two primary design challenges. First, calculating the correct angle of the sun in real time so that the panel can always face it optimally. Second, creating a mechanism that allows the panel to rotate in any orientation, maintaining a perpendicular angle to incoming sunlight for maximum energy capture. To address these challenges, we gave ourselves the objective to create a system of two modules: the compute module, responsible for all the calculations and logic, and the solar module, performing the physical reorientation of the panels, allowing for easy scaling and testing. The design itself opens opportunities for real-world applications. The modular nature of the system makes it valuable in both energy and educational markets. In energy, it can be scaled to enhance solar farms or residual systems. In education, the model serves as a hands-on exhibit to inspire students, showing the potential of engineering solutions to make renewable energy more efficient.
At the beginning of our design phase, we wanted to ensure that we followed the general and specific design specifications as guidance. The general, which includes exhibit must contain one or more automated features within its display, assigns a floor area of 8 feet by 10 feet and is not exceeded, must not exceed either the new materials budget of $150, and should engage and be interactable to children of all ages between 5 to 18 years old. The specifics being: panel on solar module must weigh under 2 kilograms to fall below the servo failure limit, and the panel rotation should avoid tangling of wires and looping on itself.
And that's what makes our system really stand out. We took a hard look at two major flaws in conventional solar trackers. First, most designs rely on just two motors, one for pitch and one for yaw, which is causing the wiring to twist over time and limits the panel movement. Secondly, even if one motor fails, the entire system would go offline.
So we redesigned the architecture to tackle both of these issues.
Our solution uses a dual pair servo setup, with one pair handling the pitch and the other managing roll.
This creates a channel in the middle which allows for easy wire management.
This allows us to avoid the issues of our wires getting pinched. Additionally, the use of two pairs of two servo motors increases our reliability. This is due to the fact that even if one servo were to fail from each pair, our panel could still move in a degraded state. This also adds value through a smoother motion and reduced maintenance. This design directly supports the theme by demonstrating innovation, efficiency, and improved performance in renewable energy technology. This is a deconstructed view of our system featuring the compute module and solar module with all key components visible. The main LCD screen connects to the Arduino via the digital I/O pins, enabling real-time display. The motor control board, also connected to the Arduino, receives supplemental power from a pack of 4 AA batteries. Each servo motor is wired to dedicated pins on the motor control board for precise control. Aside from the battery pack, the entire system runs on a single USB Type-B connection, keeping the setup compact and efficient. Before demonstrating our solar tracking prototype, we'll first walk through the code that powers it. The program begins by initializing the servo motors in the onboard display, then enters a continuous loop that calculates the optimal servo movements based on the incoming light data, while updating the screen with real-time information. On startup, the system briefly calibrates to the ambient light to set a natural baseline, then transitions into an active tracking mode. From there, the panel continuously follows the directed light source, which will simulate the movement of the sun, while the display reports the energy output with slight variations caused by panel adjustments. If the light source is removed, the system automatically enters a fallback mode in which the panel reorientates itself to face straight upwards. This behavior mimics a fixed floor panel and ensures the system can still collect energy even when tracking is not possible. By including this fallback, the system can remain stable and functional despite changes in lighting or environmental conditions.
Throughout the project, our design evolved steadily, with each version improving on the last. Our original concept placed the Arduino and all sensors within one unit capable of tracking light on its own, but this approach proved to be inefficient. It would have been more expensive to scale, offered limited customization, and forced too many components into a small area. The most significant change was moving from a single, all-in-one package to 2 distinct modules. By separating the system into a compute module and individual solar modules, we achieved the same functionality while making the design more flexible, easier to expand, and far cheaper. Especially since in our modern design, only one Arduino is needed to control multiple solar units.
Even after completely finishing the project, one of the biggest challenges we faced wasn't the actual engineering itself, but the time management. The schedule gave us plenty of time to design, but not nearly enough time for assembling and testing the actual system, which made the final stages more stressful than they needed to be, especially with the 3D printing being incredibly difficult to access and the different tasks taken away from valuable group efforts. From this, we learned how important it is to start building earlier and leave room for troubleshooting. If we were to do this again, we would begin prototyping much sooner and organizing our roles more clearly, so each part of the system develops at the same pace. This project showed us that effective planning is just as important as the actual technical work.
In conclusion, our innovation delivered exactly what we set out to create, a low-cost modular solar tracking system while improving how efficiently solar panels capture sunlight. We showed that splitting the system into 2 computing and solar modules, avoiding wire tangling, and keeping everything scalable can make solar energy more economical and efficient. Moving forward, we will refine tracking accuracy and expand support for more modules, but overall, this project proves how innovation can directly support the grand challenge of making solar power more efficient.